Hello friends, in this video lecture we will see shortest remaining time first scheduling algorithm with example. The shortest remaining time first scheduling algorithm is also known as preemptive shortest job first scheduling algorithm or preemptive shortest job next scheduling algorithm. In this shortest remaining time first scheduling algorithm, the processor is allocated to the job closest to the completion, but it can be preempted by a newer ready job with shorter time to completion. This shortest remaining time first scheduling algorithm is impossible to implement in an interactive system where required CPU time is not known in advance. In this shortest remaining time first scheduling algorithm, the process which is having shortest remaining time is executed first and completed. Before completion of the particular process, if another process is having shortest burst time or shortest remaining time enters in a ready queue, the current running process is preempted and new process is executed. There is a process in the running state and there is another process which is new process requires less time to execute than the running process. In that case, CPU will be taken away from the running process and will be assigned to the new process. It is often used in a batch environments where short jobs need to give preference. Let's have the example of shortest remaining time first scheduling algorithm. Find average turnaround time and average waiting time for below processes with given arrival time and CPU burst time under shortest remaining time first scheduling algorithm. To compute turnaround time, we have to compute completion time. Means turnaround time equals to completion time minus arrival time. And to compute waiting time, we need turnaround time. That is waiting time equals to turnaround time minus CPU burst time or execute time. We are having 6 processes with given arrival time 0, 1, 2, 3, 4, 5 with burst time which is mentioned there in the last column. Here to compute completion time, we have to sketch NAT chart first. Here at 0, there is only one process in the ready queue which require 7 units to complete. Means at 0, CPU will be given to process P1. So at 1, there is P1 process which is there in the running state and there is another process P2 process which is new process require 6 to complete. So here running process that is P1 requires 6 units to complete and P2 which is new process require 6 units to complete. So there is tie as far as the burst time is concerned. In this case, priority will be given to the process which come first. Means P1 will continue to execute for 1 unit because at time 2 there is arrival of another process. Means at 2 there is process P1 which require 5 units to complete, that is remaining time. P2 process require 6 units to complete and new process which is P3 process require 3 units to complete. As far as the policy of shortest remaining time first scheduling algorithm, CPU will be preempted, that is taken away from process P1 and will be given to process P3 which is having shortest remaining time. Means in NAT chart there is P3. P3 will take CPU for 1 unit only, because at 3 there is arrival of new process, that is P4. Means at 3 there is process P1 require 5 units to complete, P2 require 6 units to complete, P3 require 2 units to complete, and new process, that is P4, requires 1 unit to complete. So here P3 is actually running process, and as far as the policy of shortest remaining time first scheduling algorithm, CPU will be taken away from process P3 and will be given to process P4, and P4 will hold CPU for 1 unit. After completion of process P4, that is at 4, we are having process P1 requires 5 units to complete, P2 requires 6 units to complete, P3 requires 2 units to complete, and there is a new process P5 requires 2 units to complete. So here there is a tie between process P3 and P5 as far as the remaining burst time is concerned. In this case, priority will be given to process P3. So CPU will be assigned to process P3 for unit 1. Means at 5 there is process P1 requires 5 to complete, process P2 require 6 to complete, process P3, which is running process, requires 1 unit to complete, process P5 requires 2 units to complete, and new process, that is P6, requires 1 unit to complete. Again there is a tie between process P3 and process P6 as far as the CPU burst time is concerned, and here priority will be given to the P3 because P3 comes first. So P3 will continue to execute for time 1 unit. After completion of P3, that is at 6, there is process P1 requires 5 units to complete, process P2 requires 6 units to complete, P3, which is completed, P5 requires 2 units to complete, and P6 requires 1 unit to complete. Here CPU will be assigned to process P6 for 1, which is CPU burst time. After completion of process P6, CPU will be assigned to process P5 for how much time? 2, that is 9. And after P5, CPU will be assigned to process P1 for unit 5, that is 14, and after completion of process P1, CPU will be assigned to process P2, which is last process, for 6 units. So total time is 20. Here total burst time is 20 and completion time at NAT chart is 20. So compute completion time for each process. Process P1 completes at 14, process P2 completes at 20, process P3 completes at 6, process P4 completes at 4, process P5 completes at 9, process P6 completes at 7. So turnaround time is completion time minus arrival time. For process P1 turnaround time is 14 minus 0, that is 14. For P2 it is 20 minus 1, that is 19. For P3 it is 6 minus 2, that is 4. For P4 it is 4 minus 3, that is 1. For P5 it is 9 minus 4, that is 5. For P6 it is 7 minus 5, that is 2. So total turnaround time is 45 and average turnaround time is 45 divided by number of processes, that is 6, equals to 7.5. Now compute average waiting time. To compute average waiting time, compute waiting time for each process, which is equals to turnaround time minus burst time. Here for P1 waiting time is 14 minus 7, that is 7. For P2 it is 19 minus 6, that is 13. For P3 it is 4 minus 3, that is 1. For P4 it is 1 minus 1, that is 0. For P5 it is 5 minus 2, that is 3. And for P6 it is 2 minus 1, that is 1. Total waiting time is 25 and average waiting time is 25 divided by number of processes, that is 6, which equals to 4.166, that is 4.17 after rounded up. So in next video lecture we will try to solve more problems based on CPU scheduling algorithm. Stay connected with me. Thank you for watching. Have a nice day.